Okay, so this lab is about the spectroscopic analysis of Kool-Aid dyes. So you probably know this, but Kool-Aid contains a variety of artificial colors and flavors. A variety of Kool-Aid packets shown here, and I don't know which one you personally looked at, but we're going to talk about all of them. So shown on the right here are the chemical formulae, structural formula of the different F, D, and C dyes. So these are food dyes that were approved by the Food and Drug Administration to be put into food because they are not harmful, probably. Although you should probably avoid them if you can, just in case. So there's a green and there's an orange in there and there's a couple of reds, but the most common ones are red and blue and yellow, and those are the ones that are going to be present or not in the various Kool-Aid samples. So there are two common forms of red, red 3 and red 40. Two common blues are blue 1 and blue 2. And two common yellows are yellow 5 and yellow 6. And we have the purified food dyes, and we are going to, they have very characteristic visible spectra. And so we can use their spectra to determine which dyes are present in the various Kool-Aid samples. So just a small intro or recap of the electromagnetic spectrum, which you see here. On the left side, starting with gamma rays, are the shortest wavelength and highest frequency, highest energy light, followed by X-rays, ultraviolet light, and then the visible region is in the middle. That's defined as the region that we can see. And then infrared light, microwaves, and then the longest wavelength, shortest frequency light are radio waves. So in the visible region, you can divide that up, and that's sort of expanded and brought out at the bottom of the image here, where the violet region of the visible region is just adjacent to the ultraviolet. That's not a coincidence. It's named ultraviolet because it's just below violet. And then infrared is just to the right of the red region, right? And so depending on the wavelength, right, you can see that and the visible region varies from about 350 or 400 to about 750 or 800. And it depends on the person. Some people can see 350 nanometers as violet light, and for other people that's invisible to them. So it varies a little bit with people's eyeballs. But you can see, for example, orange light is at about 650 or so nanometers. Okay, so we're going to talk about the different wavelengths and how that correlates to the different colors of light soon. And then we'll talk about how that correlates to the different colors of the Kool-Aid samples as well. Okay. Now, light that comes from the sun is considered white light. So that's basically all of the visible light together. Now, of course, there's also ultraviolet waves that come from the sun, but if we're only talking about visible light, then what comes from the sun is white light. So that's all the wavelengths mixed together. And we can use like a diffraction grating, or the instrument itself can separate white light into different components, into the different colors, right? So that's kind of like what a rainbow, what the particles of droplets of water do in a rainbow, right? Now we're going to look at, this is an example of the full spectrum of lime Kool-Aid. Okay, so this is the absorbance scan, where you can see absorbance along the y-axis and wavelength along the x-axis. And whenever there is a heightened absorbance by the sample, then you see what we call a peak, right? So the absorbance goes up, right? So we're going to restrict ourselves to the visible region of the spectrum, and the spectrophotometers we have are actually capable of measuring more than the visible region. So to acclimate you, this is the visible region, and that spans about what you see from 400 nanometers to 750 nanometers. Now remember, so that's about here. Okay, so we're actually going to go down to about 350 probably. Now remember, if we go back to our picture of the entire electromagnetic spectrum, just to the left of visible is ultraviolet, that would be here. Just to the right of visible is infrared, that would be here. So we're going to ignore those for now because we can't see them. Zoom in on the visible region, which is here. So we see two peaks. One is around 420 or so nanometers, and the other one is at approximately 630 nanometers. Now, if we compare this scan to the scans of the dyes that we think could be in lime Kool-Aid, so I'm pretty sure that lime, since it's green, is going to have some combination of blue and yellow. Start by comparing the two yellows to the lime Kool-Aid scans. So yellow 5 has a wavelength, a peak in its spectrum at about 425, 420 or so nanometers, and yellow number 6 has a peak at about 480 nanometers. Yellow 6 is actually more of an orange color. And so it looks like yellow 5 corresponds much better with the lime Kool-Aid sample. If we look at the two blues, blue number 1 is they actually are both, the broken line didn't come out broken for some reason, but blue 1 is the one that you see here, that sort of, that overlaps well. It's about 625, 630 or so nanometers. Blue 2 is a little bit further to the left at about 600 and maybe 20 nanometers. That didn't come out as a, really sure why. But when we compare all 4 of the possible food dyes with the lime Kool-Aid, it appears that blue 1 and yellow 5 are the two components of that make the color in the green Kool-Aid. Now if we move on to grape, this is the scan for grape. So if we look at the reds, red number 40 is the one that has this sort of strange looking peak that almost looks like two peaks together, right? It has this weird profile is what we would call it. And then red 3 is the broken line, and that doesn't appear to overlap at all with the grape Kool-Aid very well. And then if we compare the blues again, blue 1 appears to overlap pretty well and blue 2 does not. So it grape Kool-Aid, if we compare these 4 with the grape Kool-Aid, it appears that grape Kool-Aid is composed of blue 1 and red 40, just based on how well the spectra overlap. Now if we move on, black cherry Kool-Aid is kind of interesting. I measured it, so if you look at the sort of dotted line, that's what I got when I put in a sample that wasn't too concentrated, wasn't too dark, and I got a relatively good peak at about 500. But then there's a peak there at about a little tiny one at maybe 630 or so, and I wanted to really see that peak and make it really big. So I put a lot more in the solution and I collected it again. So the really jagged solid line at the top is the same sample, it's just much more concentrated. So this first peak at about 500 nanometers, the big broad peak, is completely useless in the big jagged solid line sample because it goes beyond the limit of the spectrophotometer. Whenever the peak gets noisy and jagged looking like that at the top, it's not really usable. It's only when the peak is nice and smooth looking that you can really use it. And that's just because we've gone beyond the limits of the spectrophotometer. All instrumentation has limits, and you can't exceed the limit of the instrument. But I did want to get a bigger peak for that sample on the right. Now black cherry is mostly red, but it does have a little bit of a purple tinge, and so I think it's probably mostly red with a little bit of blue in it. So if we overlap those, these are the two reds. We have red 40, which appears to match pretty well, and red 3, which does not match very well. So, and then if we compare the blues, again, blue 1 is the one that appears to overlap in terms of its lambda max. Its wavelength of maximum absorption is at about 630, 625 nanometers, and that lines up pretty well with the black cherry Kool-Aid peak. But the blue 2, which is a little to the left, is more like 610 nanometers or so. It's definitely doesn't seem to overlap as well. So I think that the black cherry, when I compare all 4 of the possible dyes, like the grape, right? If we go back, it's like the grape, except it just has a far smaller amount of blue, which makes sense because black cherry is mostly red, a tiny bit of purple, right? Now tropical punch Kool-Aid looks like this, and so again, I collected 2 scans, one with a sort of good amount of red, and then I increased the amount just so that I could see if there were any tiny peaks in there anywhere that were maybe a smaller amount of blue 1, because tropical punch is red, but it might have a little tinge of purple. So I compared it, and based on the spectra I have, it appears that it contains only red 40. Right? I don't really see much of a peak over there at about 630 nanometers or so. However, when you look at the ingredients, it says it has red 40, and then near the end it does say blue number 1, but it must just be such a small amount that it's not detectable by our spectrophotometer, right? Certainly based on my results, I would say it's only got red 40. But we checked, we tested it, we just couldn't see it. So we would need a much more sensitive instrument to determine that. Or we could just read the ingredients. Now, cherry Kool-Aid looks like this. Check the ingredients. It also doesn't have, it doesn't list anything other than red. Mixed berry, it's listed here as mixed berry, but on this little line here it says blue raspberry. So I don't know if that's colors or if I just thought it was blue raspberry. But anyway, this blue raspberry or mixed berry appears to be just blue number 1, no blue 2, and no other color. See, if we move on, here's the orange Kool-Aid. Now, orange is probably a red and a yellow mixed together. Look at the first. We'll start with the yellows. The yellow 5 appears to overlap very well with the peak from the orange Kool-Aid, with a very large amount of that peak, right? And then yellow 6, I don't know. You know, it could have some yellow 6 in it. I can't rule that out. Certainly yellow 5's peak overlaps very well with the orange Kool-Aid peak. If there is some yellow 6 in there, it's definitely underneath this peak. It's really masked by this by the profile of the orange Kool-Aid peak. I can't really rule out yellow 6, but if I had to pick one of them, I would pick yellow 5. Now if we put in red, red 40 appears to overlap with the peak at about 525, 530 nanometers. This one, the orange Kool-Aid actually, it has this large peak in the yellow region, or it has this large peak from the yellow dye, and then it has a very small peak from the red dye. And part of the problem is the red dye and the yellow dye, their peaks are so close to each other that they almost look like one giant blob. And so this one's really hard to analyze, I would say. So red, this one appears to have red 3, but it's hard to say. So I don't know. Peaks are so close to each other, right? But based on the ingredients, now I'm going to put them on there and I can see, yeah, I believe that those peaks are there. But you guys see that those 2 peaks in the orange Kool-Aid are so close to each other that it's really hard to analyze this spectrum. Maybe better to separate this one using chromatography and then run the individual purified dyes separately. All right, now one last thing I want to talk about is, so here we have visible scans of red, yellow, and blue food dye. All right, so the yellow dye is shown in the color yellow, and the red dye is shown in the color red, and the blue dye is shown in the color blue. So these appear yellow and red and blue to our eyeballs, right? But if you look at the top, you know, the yellow dye absorbs at about 430 nanometers, which if you look at the top, that's actually a blue region of the spectrum, right? It's kind of a bluish violet. The red absorbs at about 525 nanometers, and 525 nanometers is green light. And then the blue dye absorbs at about 630 nanometers, which is orange light, right? So the color that you see is not the color of light that is absorbed. And the reason is because as white light travels through the dye, then some color is absorbed. And then what remains comes to your eyeball. It is what's left from the white light, right? So the color that's absorbed is not the color you see, right? It's the complement actually of the color you see. So if we look at that, yellow number 5 absorbs maximally at 425 nanometers. That's violet light. Red number 3 absorbs maximally at 530 nanometers. That's green light. And blue number 1 absorbs maximally at 630 nanometers. That's orange light. Now if we compare, if we relate how blue relates to orange and how red relates to green and how yellow relates to violet or purple, they are complementary colors. Okay, so if we look at each dye appears one color but absorbs a different color. Now if we the color wheel, complementary colors lie across from each other. This is the same color wheel you'd use in art class. So yellow solutions absorb violet light, which is on the right, which is on the opposite side. Red solutions absorb green light, which is on the opposite side of the wheel, and blue solutions absorb orange light, which is on the opposite side of the wheel. So the take-home message here is that complementary colors lie across from each other on the color wheel. The color that is transmitted by a solution, which your eye sees, is complementary to the color that is absorbed by the solution. So it's sort of what comes out, what's left over from the light after what's absorbed is taken away. Okay, because remember, what's absorbed is taken out of the white light. The sample absorbs it, and then it only lets through what's not absorbed, which is what your eyeball sees.